Hi, I'm Jay Thompson with Thompson Communications. Welcome to my video series about two-way radio that I call Radio 101 for public safety users. I put this series of videos together so police, firefighters, and paramedics would have an idea what happens between the time they hit the push-to-talk button on the radio out in the field and the dispatcher finally gets to hear the audio at the console. Hope you find it interesting. Graphics are courtesy of Tom Dover with Dover Training Solutions. We're going to cover common terms, signal propagation, and more importantly, signal loss, and try to show you how to avoid it. Here's some of the common terms you'll hear RF techs use. Decibel is the one used most often. That's a gain or a loss measurement. Logarithmic, not linear. 3 dB loss is 50% of your power. 10 dB loss, you're down to 10% of your original power. dBm is referenced to a milliwatt. This is an actual signal strength measurement versus dB, which is a ratio between two values. Frequency you're probably familiar with. Hertz is the modern name for cycles per second. You're probably more familiar with kilohertz for AM radio and megahertz for FM radio. Gigahertz is something you're going to hear as 5G comes into play. RF simply means radio frequency. You may hear referred to an RF tech or RF energy, RF wave. These are the public safety frequencies assigned by the FCC. Low-band systems have pretty much gone away. VHF and UHF are still popular in rural areas because they provide better coverage than 700 and 800 meg trunk systems. Paging systems are usually VHF because they provide better coverage and also have higher power transmitters authorized. The T-band is a section of UHF frequencies used in a small number of major metropolitan areas. Originally, a few years ago, Congress was going to take this away, but just in the last couple of months, they've changed their mind, so these frequencies are still available. Here's a diagram of a wavelength. It's just one cycle of RF energy measured in meters. The symbol lambda is the inverted Y symbol that we use for wavelength. 300 divided by the frequency in megahertz gives you the wavelength. You may have heard about 2 meters if you're into ham radio. That's 150 megahertz. Because the amount of RF energy is equal in the top and bottom halves of this cycle, antenna lengths are based on 1/2 wavelength. That's all that's needed to capture enough energy to process the signal. The left side shows one wavelength at 300 megahertz. It takes 0.0033 seconds to pass one cycle. At 3 gigahertz or 3000 megahertz, we pass 10 cycles in the same time frame. Because the frequency's gone up by a factor of 10, the wavelength is decreased by a factor of 10. This shows why we get more data throughput or bandwidth at higher frequencies. We just saw as frequency goes up, the wavelength goes down. Antenna lengths are based on wavelength. Mobiles and portables are usually a quarter wavelength. Here's some common sizes for public safety frequencies. I highlighted the 150 and 450 in red to point out a 3 times increase in the frequency is a 3 times decrease in the antenna length. RF energy dissipates as it travels just like light does, based on frequency and distance. An interesting fact is that RF energy loses 36 decibels leaving the antenna. That means it's at 1/4000th of the original power as soon as it gets out of the antenna and into the air. Give you an idea how RF energy propagates, I put a 1-inch circle on this balloon. You can see it's pretty dark. Once I blow the balloon up, you'll see how the ink expands across the face. Now the ink's about 2.5, 3 times diameter it was before. Even though the amount of ink hasn't changed, it's just spread over a wider area, so it's less dense. RF acts the same way. If you double the frequency or the distance, the signal strength is reduced by 6 decibels, 1/4 the original power, not 1/2 like you'd think by doubling. Just like sound, low frequencies travel further than higher ones. This chart shows distance loss for 100 decibels at 40 megahertz. It's almost 37 miles to lose 100 decibels. VHF can only go 10 miles before it loses 100 decibels. UHF is about 3.5, and 860 meg is 1.7 miles. Non-low band frequencies are considered line of sight. This is because they don't follow the Earth's curvature. Low power at height can beat high power at ground level because of line of sight considerations. International Space Station has ham radio operators on board using a 5-watt portable at 2 meters, talking to ham radio operators on Earth. This is from an altitude of about 250 miles, all because it's a clear line of sight. RF has less attenuation over water because there's no ground clutter. This could come into play if your agency uses LoJack. You might have a very strong signal from a stolen vehicle and think it's within a couple hundred yards, but it could be across a bay or a lake because the signal propagates so well. Two-way radio signals are vertically polarized. That means the antenna is pointed straight up. You get the maximum energy transfer when both antennas are vertical. In theory, nothing is going to happen if one's at 90 degrees to the other, but in practicality, there is energy transfer at a much weaker level. Depending on the distance between the transmitter and receiver, a portable radio can have 18 decibels of loss if one antenna is cross-polarized to the other. That's 1/64th the signal strength being received. There's some typical power levels for two-way radios. As you can see, the portable's always the weak link, and the number of tower sites is determined by the uplink signal strength. Uplink is from the field unit back to the repeater or tower site. Portables have a poor ground plane, so their effective radiated power is usually about half of what is rated for the transmitter. Attenuation is just another word for loss rated in decibels. Obviously, a radio on the hip is going to transmit much further away from your body than through it. Everything attenuates RF. Concrete and steel buildings are going to be the worst situation. These next two slides are going to demonstrate signal attenuation at 860 megahertz. We're going to assume a 100-watt repeater, which is the same as 50 dBm. At 10 miles, we lose 115 decibels due to attenuation. That means the portable is going to have a received signal level of minus 65 dBm. Now the receiver works down to minus 120, so this gives us an operating margin, or sometimes called a fade margin, of 55 decibels. But coming back, because the portable is only effectively probably putting about 1 watt or 30 dBm, the receive site seeing a negative 85 dBm signal level. This is 35 decibels of fade or operating margin. These numbers are for ideal conditions, and RF doesn't see ideal conditions in the real world. E-glass or low E-glass is energy efficient, but it has a high RF attenuation factor. It's easy to notice this because it has a blue or green tint. This is a real-world example of an energy-efficient building attenuating RF. The yellow circle on the left is the county courthouse in Chester County, Pennsylvania. The right-hand circle is the transmitter receive site. It's 2.4 miles across, but users had a very hard time getting to the site, even though they could look out the windows on the east side of the building and see the transmitter site. This is from a spectrum analyzer, a device that shows RF energy levels. The left-hand side of the screen is 80 megahertz, the right hand is 110. So what you're seeing is the FM broadcast band. Each spike is an FM station. As I animate this, you're going to note that the signal strength tends to fade. This isn't due to any movement on the antenna's part. This is just how RF propagates through the air. This series of slides is going to demonstrate how important it is to keep the radio pointed straight up and how height helps increase the received signal level. Here I'm holding a portable 5 feet above the floor, as you normally would do talking directly into the radio. The spectrum analyzer is seeing negative 85 dBm signal strength level. Here all I did was turn the portable parallel to the floor, so we're 90 degrees from vertical. The signal strength is now down to neg 92.5 dBm. This is a 7.5 decibel drop, or 63% loss. The red line was our original value. Here the radio's at floor height and it's still horizontal. Worst case scenario, minus 100 dBm, 15 decibels down from where we started, or 97% signal loss. Normally you wouldn't have a radio lying parallel to the ground at floor height, but if you're a SWAT team sniper and you're in a prone position, that could happen if you've got the radio on your hip or maybe in a tactical vest. Chances are the antenna is more likely going to be parallel to the ground than pointed straight up. Here all I did was turn the radio back vertical. It's still at floor height, but you can see we gained 6 decibels or 4 times better signal strength than what we had when the radio was parallel to the floor. I know it's tempting, grab the antenna, pull the radio out of the charger or your holster, but avoid doing that. This connection in here is designed to pass RF. It's not really designed to be a strong mechanical connection. If this gets broken or goes intermittent, then the RF isn't going to get out the antenna and nobody's going to hear you. Even if you had 100 watts in here, if it can't make it to the antenna, it's not going to propagate. This Uhf Kenwood came apart when I was on a deployment last year. It shows you a couple things. First off, here's a 3-inch housing. That's how you get a 6-inch UHF antenna. You just coil up the wire. The other thing that was interesting is this unscrews, and after about 3 turns, it's completely off the stud, which connects to the antenna connector going into the radio. So you want to keep that in mind next time you grab the antenna and use it as a handle. Could be breaking this connection in here. That gets intermittent and it becomes very hard to track down a problem. Here's a summary from today's video. Talking directly into the portable or using a speaker mic with an antenna beats the radio down on your belt. There aren't many speaker mics with antennas anymore. Those went away once Bluetooth came out. In a real jam, you can hold the portable overhead and use your speaker mic. That extra 2 or 3 feet and clearance from your body could make the difference between hitting the repeater or not. Antennas work best straight up. Don't use the antenna as a handle. In the worst case scenario is sitting in a vehicle with your radio on the belt next to the door. Thanks for watching. If you got any questions or comments or ideas for other videos, I'd love to hear it. You can get a hold of me at support@tacticalrf.com.